Hello, guys. How are you doing?
Good afternoon, Professor.
Nice to see you.
Hi, Professor.
Hi.
How are you doing?
Okay, yeah, not bad. Thank you. It's kind of already raining and cloudy, cold. Weather is really not like summer anymore. A bit sleepy. Okay. Well, I guess those who still want to join, they will join on the way. Any questions regarding our previous material which we discussed?
Excuse me, Professor, can I ask a question regarding the rocket launcher example? So you said that we can consider the momentum law with only projection of x-axis.
Yeah, in that case.
So we don't consider y-axis, and we because of external forces or force of gravity, because it's not isolated system.
No, so force of gravity is compensated. So if we consider only along the axis x, the force of gravity is compensated, like weight of the rocket and the platform. It's compensated by the reaction of the railways. However, we launched the rocket at some angle in horizontal plane, so we didn't have any angle with regarding the horizon. So that was a horizontal plane. And if we have two components that's why we have only two components, not three, of the rocket velocity. One along axis x, one along axis y. And definitely when we launch a rocket, we get some, provide some acceleration to the rocket. So there is some force which pushes the rocket. And according to the third law of motion, this equivalent force rocket will push our platform in other direction. So these forces will be equal to each other, but just directed in opposite, aligned in opposite directions. So that's why we have some force which is in the direction opposite to the velocity, like acceleration of the rocket. And this force can also be considered in terms of two components, one along axis x and one component along axis y. So if we consider along axis x, then nothing prevents our platform to move, because along axis x it can, without any friction with wheels, it can roll over these railways, and that's why we can consider the conservation of momentum along axis x. However, along axis y, it's fixed on railways, so it cannot move, and that's why, since it cannot move, there is a force which is applied not to change the result of the force of component y. Is not change in momentum of the system, but just to work against these railways. And that's why we cannot apply law of conservation of momentum. So we need to split this system, like all these velocities, in two components along y and x, and consider for conservation of energy, conservation of momentum, only those velocities which were before and after, but projected on axis x.
Now I get it. Thank you.
Mm-hmm. You're welcome. Okay, guys, so we have still quite many things to discuss. So probably I will now switch to our slides. And today, let's see how it goes if we have enough time. We need to continue our consideration of our cases with elastic collisions, because we considered inelastic. So when two bodies interact with each other and then kind of stick and move together. So that was the case which we considered at the end of our last class. Now let us consider another case when we have ideally elastic collision. So in general, if you're right, because the signs of so it's one-dimensional case, and signs of velocities will define either it moves along axis x or in the opposite direction. So depends on our case, either bodies move toward each other or they move in one direction. You will define the signs, but in general, we can write the following system of two equations. So if we have two bodies, then the m1 with the velocity v1 plus m2 with velocity v2 equal to m1 v1 prime, it's velocity after collision, plus m2 v2 prime. And since it's ideal elastic collision, we can also write the equation for conservation of kinetic energy, because as I mentioned last time, when we have ideal elastic collision, we don't transform kinetic energy into internal energy, and that's why kinetic energy is conserved. So in this case, m1 v1 square divided by 2 plus m2 v2 square divided by 2 equal to m1 v1 prime square divided by 2 plus m2 v2 prime square divided by 2. So we have a system of two equations, and for instance, if masses 1 and 2 are given and initial velocities v1 and v2 also given, then since we have system of two equations, we can solve them for unknown v1 prime and v2 prime. So this is a very standard approach, and that's allowed because we can apply simultaneously two laws of conservation, momentum, and kinetic energy. So sometimes it's written in a bit different form, kind of a bit simplified, can be useful. So let's do the following. Let's multiply this second equation by 2 and group everything what is related to mass 1 in the left and mass 2 in the right. So it will be m1 multiply v1 square multiply, minus v1 prime square. It is equal to m2 v 2 prime square minus v2 square. Yes, now it is actually the difference of squares, so we can transform it. It will be m1 v1 minus v1 prime times v1 plus v1 prime. And it's equal to m2 times v2 prime minus v2 v2 prime plus v2. Okay, now let us also rewrite equation 1 in a bit different form and write it here. So it will be also grouped by m in the left and m1 in the left and m2 in the right. So it will be m1 v1 minus v1 prime equal to m2 v2 prime minus v2. And now we can divide this previous equation by the last equation. So what we get, it will be v1 plus v1 prime equal to v2 prime plus v2. And if we group them in the left velocities before collision and in the right velocities after collision, so we will get v1 minus v2 equal to minus v1 prime minus v2 prime. Okay, so this is another form of second equation which you can use. So you can use first equation in this system and this as a second equation. Then it's just easier because you don't need to deal with v in second power. And what it tells us that the difference, the relative velocity of two bodies before collision, which is this part, is equal to minus relative velocity of two bodies after elastic collision. So this is pretty much everything about this collision in one dimension, elastic collision in one dimension. And in terms of the concept, and maybe it would be good to consider one example. Let's go to another slide. And I think that most of you have seen such a kind of relaxing toy, which consists of usually has 5 balls in one axis. They are hanging on some threads, and you can tilt the first one, then let it go. It will gain some velocity and hit the rest. So as a result, it will just freeze, will stop, and the ball at the other edge will gain some velocity and will be tilted some similar angle. So it will gain also velocity v. If we consider ideal elastic collision, we don't have loss in energy. In this case, even in real system, loss of kinetic energy is not very high, so it repeats quite for a long time. So the question is, why does it happen? Why we have, if we hit with one ball, the only one ball is pushed away from the other side, and we don't observe something like this when we, let's draw it again. So this, we hit with one, and then instead of one going, 2 of them are gain some velocity, which is half of the velocity of this first ball, which hits from the left. So it never happens. You can check it. So if you hit with one ball, only one ball is reacting at the opposite side. However, if we check the conservation of momentum with this second case, which we ask why it doesn't happen, everything will be okay. So let's write it. Assume that mass of the of each of these balls is the same. Then we can write that mv, so this velocity of our first ball with which we hit from the left side, is equal to 2m, because let's say we have the case, the second case, when 2 balls react, times v divided by 2. Then 2 and 2 we cancel out, and it's equal to mv. So everything is okay for this particular example. Momentum is conserved, but it doesn't happen, and it doesn't happen because of one reason. Do you have an idea what is the reason for that? Has someone any guess? So, as I mentioned before, we consider this system, this interaction, as ideal elastic collision. And if we have ideal elastic collision, we need also take into account not only conservation of momentum, but also conservation of kinetic energy. So let's see what happens here. We have what kinetic energy we have at the beginning. It's mv squared divided by 2. And then assuming that two balls react into this collision, then we should get something like this. It will be 2m, then v divided by 2 square, and here divided by 2. So we have two masses, and instead of velocity, we put half of velocity, which satisfies the conservation of momentum. So now 2 and 2 we cancel out, and we get mv squared divided by 4. So definitely mv squared divided by 2 is not equal to mv squared divided by 4. And that's why the conservation of energy, or kinetic energy, is not realized in this second case. So this never happens. We have only, if we hit with one ball, only one ball reacts. If we hit with two balls react. And you can think just in some free time what will happen if we glue these two right balls together so they cannot detach from each other. What will happen if we hit it with one ball from the left? That's kind of interesting question, but in order to explain why it happens, how we observe it, we need to explain it that since it's elastic collision, we need to take into account both simultaneously conservation of momentum and kinetic energy. Okay, let us go further with collisions in multi-dimensions, in 2 dimensions. So I mentioned before that law of conservation of momentum in case of an isolated system is valid in its projections on x and y. So we take projections of momentum in the on axis x, the sum of these projections. So this parameter should be constant. And also the sum of projections of momentum on axis y, and this also should be constant. So taking this into account, let us consider the next example. Maybe let's go to another slide, it will be crowded. Okay, let's have some mass M1, some mass M some mass M2, and initial velocity of M2 is 0, and initial velocity of M1 is some like value V1. Okay, and it's directed along axis X. So let's draw a system of coordinate. Axis X, axis Y. So let us assume that here is the point of collision where they collide. And after this collision, so it was at some angle, not one-dimensional case, these two bodies move at some angles after collision with respect to axis x. So we have M1 in this direction, which is described by angle theta, and mass M, like body M2, in this direction. Here is angle alpha. Or no, let's let it make okay, this is our body, and this alpha, or this angle, let's call it phi. Okay, theta and phi. Now we need to consider these projections on axis x and y and get respective system of equations which can describe the behavior of this system under elastic collision. So let us consider first axis x. For axis x, we have initial momentum, which is m1 v1. So it's velocity of the first body which hits the stationary immobile body m2. And this will be equal to the projection of this. So here I forgot to write, it's v1 prime, and this is v2 prime. And here everywhere we should put vectors because it's already a case with 2 dimensions. But here where we consider projections, we don't put vectors because it's projection on axis x. So then we can write that projection of this momentum of body m1 after collision on axis x will be m1 v1 prime times cosinus theta. The same we can do for the second body, will be plus m2 v2 prime times cosinus phi. Then we consider projection on axis y. So initially in the direction of axis y, we didn't have any momentum because momentum of body 2 is equal to 0 and momentum of first body is fully or like arranged along axis x. So projection on axis y is 0. But after collision, we get some components, and that will be m1 v1 prime times sinus theta. So it's this component of momentum of velocity, like it's v1 prime times sinus theta. And we need also to subtract component of momentum of body m2 after collision because it is directed in the opposite way. So it's goes downwards in the opposite direction of the axis y. So it will be m2 times v2 prime times sinus p. Okay, and since we assume that this is elastic collision, we also can write equation for the conservation of kinetic energy. It will be m1 v1 square divided by 2 equal to m1 v1 prime square divided by 2 plus m2 v2 prime square divided by 2. So now we get system of 3 equations, and that means that we can solve it with respect to 3 unknown parameters. So it could be, for instance, unknown v1 prime, v2 prime, and one of the angles, so theta or phi, or some other combination. Usually you have given m1, m2, and v1, and then there is a different combination of possibilities for unknown parameters to be determined after elastic collision in two-dimensional case. Okay, I guess this part is clear. Yeah, you don't have any concerns or questions? Let's maybe have some example of this collision into dimensions. Let's consider a cross section, like T-type cross section. So in this case, it will be inelastic collision. Let's have 2 cars. With M1 V1 and M2 V2. Then they collide with each other at this point. Here we put the system of coordinates, and let's assume that these 2 cars, after collision, they stick to each other and move together with some velocity vector v. So the question will be, which we want to figure out, what will be the orientation of this vector? Means what will be angle, let's say alpha, with respect to horizon, and what will be the magnitude of this velocity. So let us consider the projections of momentum before and after on axis y and x. So let us start from axis x. So along axis x, our first car is moving, is M1. So for its projection, for the projection of its momentum on axis x, we get M1 V1 equal to the sum of 2 masses, because these cars kind of stick to each other, will be M1 plus M2. So this is momentum along axis x after collision, will be V times cosinus alpha. And the same we can write for y. It will be now along axis y, initially we have m2 v2. And that is equal to m1 plus m2 times v times, not cosinus, now it's sinus alpha. So in order to get the angle, the direction of this resultant velocity, what we can do, we can divide equation for the conservation of momentum along axis x by equation for the conservation of momentum along axis y. And we get m1 v1 divide m2 v2 equal, then we cancel out these parentheses with masses and velocity after collision. We will get cosinus alpha divided by sinus alpha. Oh, okay. So it would be better to divide second, like equation y divided by equation x, because then we get tangents alpha. But doesn't matter. It will be like 1 over tangents alpha. And that is the way how we get the angle, the orientation. So it's totally defined by the ratio of, in this particular case, by the ratio of momentums before collision for two bodies, for two cars. And once we determine angle alpha, we can, from any of this equation for x or y, let us consider equation for x, we can get the value of the velocity. So from this equation for x-axis, we can write that velocity is equal to m1 v1 divided by the sum of two masses, cosinus alpha. So with these two steps, by considering the equations for conservation of momentum along two axes, we first determine somehow didn't work. Okay, we first determine the angle, the orientation, and then the value of the velocity after ideal inelastic collision. So this is one of the example for application of these multi-dimensional collisions. And if everything is clear with this, I think it's good to go for next sub topic. We need to introduce center of mass. We still have some time. I don't know if we have enough time, but let's try to do what we can, and then it will be more time during the class on Friday. So if we have a system of two bodies, for instance, or many bodies, doesn't matter, we can represent, so the translational motion of this system of bodies can be described by motion of one mathematical point, assuming that all mass of the system is concentrated in this point. And this point is called center of mass. So let us learn how to calculate this position of the center of mass. So we will start from the simple case. Let's have system of two bodies. So here will be body M1, here a larger body M2. So M1 is, so this is our axis X, is located at X1 coordinate. This one is located at X2. Then we want to find some center of mass of these two bodies, which is located at a distance X center mass. So how do we do this? There is a rule how we can calculate this coordinate of center of mass. And for the system of two bodies, it's quite simple. So we have sum of products of mass to its coordinate in the denominator. Divided by the sum of two masses. So this is the way how we calculate, and you can see if M2 is larger than M1, then the coordinate of X of the center of mass will be like biased closer toward the second body. If these masses are equal, if M1 equal to M2, then X, the coordinate of the center of mass will be at the center in the middle between these two bodies. So it will be, we can write M x1 plus x2 divided by 2m. So we cancel this and we get x1 plus x2 divided by 2. So kind of very straightforward and obvious. If we have a system of many bodies along axis x, the coordinate of the center of mass will be calculated as sum over all bodies of the product of mass to its location divided by the sum of all masses. And we can rewrite it as 1 over capital M, which is sum of all masses of mass of the system of bodies times the sum of this product mass of each component to its coordinate, its location. So obviously bodies can be located not only along one axis, so they can be distributed in the space. So the same approach can be applied to y coordinate of center of mass will be total mass of the system, sum of the product of mass, each mass to its location along axis y. And the same we can write for the z axis, z coordinate of center of mass will be 1 over m sum over I, mi, z, I. And definitely that at the end, when we have some two or three-dimensional case, let's consider the three-dimensional case, the center of mass can be represented with a radius vector for center of mass equal to x cmi plus y cmj plus zcmk. So this is how we can define the position of center of mass of any system of bodies distributed in the three-dimensional space. Okay. What if we have some extended body? So it not consists of different bodies, but it's just some bulky, bulky body with some dimensions in along all axes like x, y, and z. In that case, we need to consider small pieces of this body, like small volumes, within which the density of the body can be like different conditions. It can be uniform density or also can be density as a function of coordinate of this body. But doesn't matter, we will pick up very small volume of this body within which density can be considered constant. And then instead of volume, we will consider some very small mass, which will be associated to volume defined as volume multiply density. So the coordinate of the center of mass, in this case, in the limit of delta m, like this small mass approaches to 0, so it's very small, 1 over m. So here we write the definition of how we determine the coordinate x of the center of mass, sum of I xi delta m I. So means product of position and this very small mass from the volume of the body. It will be equal to 1 over m integral x dm. So it will be, if we have some distributed bulky body, then along axis x, we need to integrate the product of the coordinate x and very small mass. So we integrate, we kind of get a sum of products for each very small piece of this body. So this is what means to integrate. The same can be written for, the same can be written for y coordinate of the center of mass. It's 1 over m integral y dm, and for z 1 over m integral z d m. And in general case, we can write that the radius vector of the center of mass is equal to 1 over m integral radius vector of position of this small mass dm, like integral over all pieces of these small pieces of this body. I guess now we will stop at this since we are running out of time, and we will start our next discussion from an example. So you will have some better feeling what does it mean to integrate these products of coordinate all over of each coordinate of small mass all over the body. So I will give you, we will recall this part so you have refresh it in your memory, and I will give you a few examples so you will feel more comfortable with this. Okay, do you have any questions now? If any questions, you ask me now, or you can ask me during our next online class, which will be on Friday at 3 p.m. Okay, guys, thank you very much for attention. Have a good evening and take care. Don't get sick. Now weather is changing, so wear proper clothes. Good. Bye.
Goodbye.
Why doesn't it change? Okay, bye-bye.